So this video, we're going to learn about how to apply a quantum theory to atoms that have more than one electron. So far we've just looked at the hydrogen atom, which only has one electron. So now we'd like to consider other atoms on the periodic table where we've got a nucleus with different amounts of positive charge and then more than one electron in that atom. So first, the bad news. So it turns out that when we have more than one electron, that we can no longer solve the Schrödinger equation exactly. Alright, so what I mean by this can't solve it exactly, we can't solve it in terms of simple mathematical functions. So it's not that we don't know how to solve the Schrödinger equation, that we just haven't figured out how to do that. It's that it actually cannot be solved in terms of mathematical functions, no matter how much people try. But we can still write down that equation and solve it numerically on a computer using some approximations. So we need better and better approximations if we want to get more and more precision in terms of the number of decimal points that we might get with our predictions for energies or locations or those kinds of things. So we can still do this. We can still solve the Schrödinger equation. We just need to make some approximations. And we need to do it numerically on a computer. So they're no longer equations, simple equations that we can write down to do this. So we just need an equation, computer that has Schrödinger's equation programmed into it along with some approximations that might get better and better depending on how well we want to do with our answer. So one of those approximations that we're going to make is something called the orbital approximation. And so here it is. It's kind of summarized in this little bullet point right here. So what we're going to do is we're going to assign each electron in an atom. So we're going to figure out how many electrons an atom has. And then we're going to assign each one to one of these hydrogen-like orbitals. So we already know about the orbitals that hydrogen has. You know, 1s, 2s, 2p, 3s, 3p, and so on, 3d. So we know about all those orbitals, and they keep going, right? Dot, dot, dot. So what we're going to do is we're going to assume that these orbitals, or something like them, still exists for atoms with more than one electron. And we're just going to modify them a little bit. We're going to assign all the electrons to these different orbitals and say, hey, I'm going to stick that electron here, and I've got another electron, well, I'm going to put it here. So we're going to assign it to these orbitals, and then we're going to see what quantum mechanics tells us about the result. So when we've assigned electrons to these different orbitals, it produces something that we call an electron configuration. So that's just a statement of where the electrons are located. So it's rather like if we were thinking about the Bohr atom, where there's a positively charged nucleus, and now maybe we've got different amounts of charge in there, and we've got these rings, so we could assign electrons to rings, and we could say, hey, we're going to stick an electron there, we're going to stick an electron there, we're going to stick an electron there. That one disappeared. Don't know why I did that. Anyway, so we could put electrons on rings. And that's kind of what we're doing here. We're assigning electrons to orbitals. Okay, so it turns out that in this approximation, once we put electrons into these different orbitals, that it causes the energies of the orbitals to shift around a little bit. And we know from the hydrogen atom that, for example, the n principal quantum number, so the shell number, like 2 or 3, the n number tells you about the energy for the hydrogen atom. But in multi-electron atoms, it turns out that the 2s and 2p subshells will have different energies. So that's what I mean by split and shift. So the energies of these orbitals will change, move around a little bit. Why? Well, it has to do with the interactions between the electrons. So we know electrons repel each other, so that interaction is going to cause the shifting and splitting of these orbital energies. So what we're going to be interested in is obtaining the lowest energy electron configuration, or arrangement of electrons. And so in order to do that, there are 3 rules from quantum mechanics that we are going to have to use. So these rules came about both from experiment and from looking at quantum theory as a way to give us the lowest energy. So when I say ground state, what I mean is lowest energy. So lowest energy will be most stable. So we're trying to figure out what arrangement of electrons in these different orbitals will give us the most stable arrangement. So these 3 rules are called the Aufbau Principle, the Pauli exclusion principle, and Hunn's Rule. But first, let's talk a little bit about how these electrons are going to shift and split. So we're going to look at this bullet point in a little bit more detail to try and understand what's going on. So let me just remind you the energy levels in the hydrogen atom. So those energies are given from quantum mechanics, or also Bohr's formula from this formula. It's negative 2.18 times 10 to the negative 18th joules. 18 joules times 1 over n squared. So you plug in the n quantum number and then you can calculate the energy of these levels. So these levels just depend on the n quantum number. So these little pictures here, let me tell you what these lines represent. So each line represents a different orbital. Remember, an orbital is connected to a wave function. So this wave function right here that's represented by this little line represents an orbital with n equal 2 because we're a 2s orbital. And because it's an s orbital, s tells us that L is equal to 0. And if L is equal to 0, the only possible m sub L value can be 0. Similarly, right here we've got 3 different orbitals, 1, 2, 3. They are all n equal 2, so these wave functions, so this wave function right here might be for n equal 2. Now because it's a p-type orbital, L will be equal to 1. And then there are 3 possible m sub L values, so maybe it's minus 1, right? So this might be minus 1, 0, and plus 1. And those would correspond to those different orbitals that we've studied the pictures for, like px, py, and pz. So each one of these is a different orbital, a different wave function that just describes the probability where you would find those electrons. And what we notice is that they all have the same energy, because energy is only determined by n in the hydrogen atom. So up here we see that all 5 of the d orbitals have the same energy as the 3p orbitals and the 3s orbitals. So remember, orbitals that all have the same energy, we say that those orbitals are degenerate. So let me just remind you of that word. So degenerate just means having the same energy. So in a multi-electron atom, what we'll notice is that these energy levels change. So here's a typical pattern for how the energies of the orbitals shift in multi-electron atoms. So you'll notice that the 1s is still lowest in energy. Then next comes the 2s. Now in the hydrogen atom, the 2s and the 2p had the same energy, but we see in multi-electron atoms that there's going to be a shifting and splitting here, so that all of the 2p orbitals have a higher energy than the 2s orbital. Then next comes the 3s and the 3p. Now you might think the 3d would come next, but it turns out that the 4s sneaks down just a little bit lower in energies than the 3d. So the 4s orbitals are a little bit lower in energy in multi-electron atoms than the 3d. So you see that some of these orbitals, the 3s, 3p, and the 3d levels, start to mesh inside these other orbital energies as they start getting close together. And so things get a little complicated up here. So that's a splitting pattern. So what we might wonder now is, well, why? So why is it that the 2s and the 2p orbitals have different energies in multi-electron atoms? And I told you it all has to do with the interactions between electrons. So let's look at some pictures to explain why that might be. So these pictures are based on what we call a simple shell or planetary model of the atom, and it turns out we can explain a lot with those kind of models. So we're going to look at both interactions between the electron and the electron that might be here and the nucleus of the atom. So there's the nucleus in UC, nucleus. So we're going to look at those interactions. We're also going to look at interactions between electrons. And occasionally we're going to find that our picture of these orbits doesn't give us the explanation that we need, and we have to use one of these quantum mechanical theory pictures right here. And so we'll talk about that picture here at the end. So first off, let's look at the effect of nuclear charge. So here I'm looking at a hydrogen atom with the electron in the 1s orbital, and here's its energy. So it's going to have an energy of negative 1,311 kilojoule. That's technically kilojoules per mole. It doesn't indicate that here, but these are all. So if you have 1 mole of hydrogen atoms, 1 mole of electrons in those hydrogen atoms will have negative 1,311 kilojoules per mole. So that unit got left off of this graph. So this next picture shows helium plus. So helium would normally have 2 electrons, but we've made the helium plus ions, so we've pulled an electron off. Okay, so what we see here is that this electron that's out here in helium is attracted to a +2 charge in the nucleus. And you might remember Coulomb's law tells us about the energy of interaction between charged particles. And so since this charge is bigger, we're going to have a stronger force on this electron, and that makes the energy a lot lower, right? So we've gone from negative 1,311 to a much lower, much more stable energy of negative 5,250 kilojoules per mole. So this is more stable, so we can see the effect of nuclear charge. So as nuclear charge increases, the orbital energy will go down. And so we know as we add more and more electrons to our atom, we're also adding more and more protons to the nucleus. That's going to cause the energies of those electrons to go down, to get lower and more stable. Now we're going to look at an effect that we call shielding. So what we're going to compare here is the helium plus ion that we just looked at that has this energy for its electrons, negative 5,250. Now what we're going to do is we're going to stick another electron in here. So now we've got 2 electrons. So the average energy of a helium 1s electron is now negative 2,372. So the energy has gone up when we added this second electron in right here. So why would that be? Well, the answer is that this electron right here that I've circled, electron B, is going to repel electron A. And so they're pushing away from each other. And so that repulsive interaction is destabilizing. So even though they both see this +2 charge in the nucleus, their repulsion is going to reduce the energy of interaction attraction that they feel to the nucleus. So that's why it's gone up. So it's gone up because of this destabilizing repulsion between electrons. One way that we could think about that is to imagine, oh, electron A doesn't get to see the full +2 charge of this nucleus because electron B over here is repelling it a little bit. So it is as if electron B shields electron A from some of the nuclear charge. That's why we call it shielding. So other electrons reduce the amount of positive charge that the other electrons feel or see. We use these anthropomorphic terms, you know, kind of imagine an electron has feelings or something, which they don't, of course. But we look at this electron and how attracted it is to the nucleus. It's attracted less to the nucleus. Why? Because electron B is repelling it. We call that shielding. So electron A is being shielded by electron B. So now we're going to look at a slightly more complicated effect, and that's called inner electron shielding. So we're going to look at this example of lithium 2+. So in lithium 2+, we have a +3 charge in the nucleus. We imagine that there's a 1s shell, and we have, this is some excited state because we've put the electron in lithium in that 2s orbital. So an electron in the 2s orbital of lithium gets to see this +3 charge. It's pretty far away, so it has a negative 2,954 kilojoule per mole interaction with that nuclear charge given its distance. Now what we're going to do is we're going to look at the energy of that 2s electron right there. So we're looking at that energy. And now we're going to put 2 more electrons in this inner shell. So in this 1s orbital, we're going to put 2 electrons in there. Now what's going on? Well, all the electrons are repelling each other, and this electron out here now sees a much lower positive charge, not just because it's further away from the positive charge, but because these inner shell electrons right here that I've just circled are repelling that outer shell electrons. This 2s electron doesn't get to see the full +3 charge of the nucleus. That charge gets reduced. Sometimes we talk about this notion of core charge, and that would be the charge that an outer electron feels. So you might write down that definition. The core charge is the charge that an outer electron might feel, and we can actually calculate that. So it's going to be the nuclear charge, minus the number of inner shell electrons. How can you tell what an inner shell is? Well, you look at the last shell, so shell number is given by the n principal quantum number. So you look at that last shell that still has electrons in it, and anything else is an inner shell. So for us, the 2s is an outer shell, and 1s would be an inner shell. But if I had like a 3s shell out here, then the 1s and 2s and 2p's would all be inner shell electrons. So we can subtract the nuclear charge from the inner shell electron. So for example, the core charge in lithium, the nuclear charge is 3, and in this case we have 1, 2 inner shell electrons. So that gives me a core charge of +1. So because of shielding, it is as if, or kind of close, to this outer shell electron not getting to see a full +3 charge, but seeing a charge that's more like +1. So you see, compared to hydrogen, where the electron also sees a +1 charge, the energy is lower in hydrogen than it is for this electron in lithium. That is in part because it still sees like a +1 charge, but this electron is further away from that +1 charge than it is in hydrogen. So that means its energy is higher, right? It's not as stable because it's further away from that +1 charge. So we say that inner electrons shield the outer electrons and sort of destabilize them a little bit. So the energy goes up. Now we want to go and answer our question, well, why is it that the 2s electron and the 2p electron don't have the same energy? It turns out that they are a little different in distance, but not very much. But it's not going to cause a big change. So let's look at this lithium atom, and we're looking at the electron that's in the 2s, and then we're imagining a lithium atom with the electron assigned to a 2p orbital. And what we see is that the energy of the electron in the 2s orbital is lower, more negative, than in the 2p orbital. So why would that be? They're both seeing the same charge on the nucleus. They're both about the same distance. Well, to answer that question, we have to go back and use one of our quantum mechanical pictures. This is called a radial distribution plot. So a radial distribution plot shows you the probability of finding an electron in a spherical shell some distance r from the nucleus. And so we have plots here of the radial distribution plot for the 2p and the 2s. So notice that the most probable distance is the top of this peak, and for the 2p, that most probable distance is a little bit closer to the nucleus than the 2s. So that would actually make you think that the 2p electron is a little bit lower in energy. But what's really interesting is that this 2s probability plot has kind of a smaller bump down here. So there's another peak down here. So this peak says that there's a small but moderate probability, so the probability isn't too small, down here that you could have an electron really, really close to the nucleus. So what we say is that the 2s electron is able to penetrate, so we call this effect penetration, is able to penetrate the core electrons. So if there are any other electrons in lithium that happen to be in here kind of closer to the nucleus, those inner shell electrons, then it's possible, because of the magic of quantum mechanics, that this 2s electron has a probability of getting itself really close to the nucleus. So penetrating inside where these inner shell electrons are. And that effect lowers its energy. So we call that a penetration effect, because the probability is moderately high that a 2s electron can get close to the nucleus. Whereas the probability that a 2p electron can get to that same distance, well, that would be that dot right here that I just drew, right? This little X right there. Trying to draw an X. Okay, so that distance, that probability is much lower than for the 2s electron. So we say that the 2s can penetrate the nuclear core, can get in close to the nucleus better than the 2p. And so that is why the 2p is higher in energy than the 2s. So these pictures that involve shielding, sometimes shielding is called screening. We'll see that in some textbooks. So shielding or screening produces some of these effects, and we worry about penetration, which you have to think about quantum mechanical pictures. Okay, so this picture, this order of these energies, we're going to need to know this. So it turns out there's an easy way to figure it out. So here's a little memory aid. So what we're going to do is we're going to list each shell in rows. So each shell is given by the n quantum number. So first you have the 1s, and it just has one subshell, the 1s subshell. Next we go to the n equal 2 shell, and there are two subshells in the n equal 2 subshell, the s and the p. Then we get to the n equal 3 shell, and there are three subshells, s, p, d, and so on. So we just make a little table like this. So like down here for 5s, we'd have 5s, 5p, 5d, 5f, 5g, and there have to be 1, 2, 3, 4, 5 subshells, so we would have these 5 subshells. Now it turns out that the G, H, I, all those other subshells are not going to become very important, so often we will leave them off our list, but in principle you could continue on listing them. So for the 6 we'd have 6D, 6F, 6G, 6H for the 1, 2, 3, 4, 5, 6 subshells in the n equal 3 shell. Okay, so to get that filling order that we listed before, what you're going to do is start at the top, and you're going to draw diagonal lines that slash down through from right to left. So first thing that we come in contact with is the 1s, and then we've left our chart. So we go back up, and we do the next thing, 2s. So 2s is going to come next, and then we do 2p, 3s, 2p, 3s, and then it's 3p, 4s. So 3p, 4s comes next, and then 3d, 4p, 5s. So 3d, 4p, 5s. And you can keep on doing this to get the order of filling for all these orbitals, and you will see that that matches up with my table that I've shown here. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, and so on. So following that little mnemonic helps us figure out the filling order. So we can reproduce the order that's on that graph by using this little trick. Okay, so now we're ready to go back to our rules here, and we're going to use this orbital approximation. We want to assign electrons to an orbital, and we want to get the ground state, the lowest energy electron configuration, and we need to use these three rules. So I need to tell you now what these three rules are. Here we go. First rule, the Aufbau Principle. So Aufbau is a German word, and it means kind of building up. So we want to get the lowest energy of the ground state orbital. So what we do is we fill orbitals, so that just means assign electrons to orbitals from low energy to high energy. So the first place we want to put an electron is down here in the 1s orbital. As we continue to add electrons to orbitals, we're going to move up higher and higher in energy. So this follows that same filling pattern in terms of energy that we just talked about. 1s, 2s, 2p, 3s, 3p, 4s, 3d, right, because we're n equal 3 here, 4p, and so on, all right? So that's how we use that. So that rule, we're going to start down here at the lowest energy, we're going to put electrons in there. So you might think that if we have an atom that has like 10 electrons, why not just put all 10 electrons down here in the 1s orbital? That ought to follow the Aufbau Principle and give us the lowest energy. Well, we have to combine the Aufbau Principle now with another rule, and that rule is the Pauli Principle, or the Pauli Exclusion Principle. And the Pauli Principle says this: no two electrons in an atom can have the same set of 4 quantum numbers. So if we're assigning electrons to orbitals, an orbital is going to have quantum numbers n, l, and m sub l, and then an electron can either be spin up or spin down, so an electron is going to have an m sub s quantum number. And what we want to make sure is that no two electrons in the atom have the same set of 4 quantum numbers. Okay, so you can analogy here. You can think of these as like seat assignments in a stadium, right? Because you have to go to a particular zone, and you're in a particular deck, and then you're in a particular section, and then you're on a particular row and in a particular seat. So these are kind of like assignments for an electron to be a particular way. So the consequence of the Pauli Principle is that only 2 electrons with paired spins, so paired spins just means that they are opposite in direction, can be assigned to each orbital. So if we represent an orbital like the 1s orbital by a little line, and we represent the spins on the electron up and down by these little arrows, so up might be plus 1/2 and a down might be minus 1/2, then after we have filled an orbital with 2 electrons, one that's spin up and one that's spin down, we can't put any more electrons in that orbital. So for example, if I tried to put another electron with spin up here, let's list the quantum numbers that this electron would have if it is in the 1s orbital. So the n quantum number would be 1 because we're in the 1s. The L quantum number, remember the letter here tells us what L is. L would be 0. The M sub L quantum number for 1s can only ever be 0. And then the MS quantum number, since I drew the arrow pointing up, would be plus 1/2. But these 4 quantum numbers are exactly the same 4 quantum numbers that I would assign to this electron that's over here on the left. And Pauli principle says that no 2 electrons in an atom can have the same 4 quantum numbers. So where did this rule come from? Well, it comes from both quantum theory in a special way, and it comes from experiments. So knowing these two things, we've figured out what this rule has to be. Okay, so that's going to help us a lot when we go to assign electrons to these levels, because I know when I put 2 electrons in any one of these little line segments like this, then I'm done, and I have to go up to the next highest energy level to put my next electrons. So now I'm done with that one. Up here, I can then start putting more electrons. All right, like that. Now there's some question about, well, where's the next electron going to go? Do I put it in the same line? Do I put it in one of these other lines? Won't go higher in energy, right? Because I haven't filled up these levels yet. So where's it going to go? In the same level or not? Well, so we need one more rule, and that rule is Hunn's rule. So it turns out that the lowest energy state has the greatest number of parallel electron spins. Parallel just means all the spins are in the same direction, all up or all down. So if we can get the electrons so that they are parallel, that's going to give us a slightly more stable atom. And this has to do with the magnetic effects. Well, it has to do in part with the magnetic effects that we get these parallel spins. So magnets sort of line up in a particular way and lower the energy when they're all sort of pointing in the same direction, all the spins in the same direction. So all up, for example. So if we have 3 lines that are equal energy, this is a more stable arrangement than doing this, where I put 1 electron spin up and 1 electron spin down in the same box. Now we already know that we can't do this, have 2 electrons that are both spin up in the same orbital. So that violates Pauli's exclusion principle. Hunn would say that's a good thing because they're parallel, but we can't also violate our other rules, so we can't violate the Pauli principle. So this is a can't do that because it violates the Pauli exclusion principle. So those are our 3 rules. So now let's do an example. So we're going to go through and try to assign all the electrons in vanadium to atomic orbitals. So first we need to look on our periodic table and figure out the number of electrons that a vanadium atom has. So we know for a neutral atom the number of electrons will equal the number of protons in the nucleus. So number of electrons is equal to the number of protons in the nucleus. And so we can figure that out by looking at atomic number. So if you look on the periodic table, the symbol for vanadium is V, and it has an atomic number of 23. That means that vanadium will have 23 electrons. So what I'm going to do is draw an orbital energy level diagram. So I'm going to write energy on this axis. So this is higher energy, this is lower energy. And then I'm going to draw those little lines to represent each of my orbitals. So here's a little line segment. There's my 1s orbital. Next, after 1s, following my little pattern that I just learned, is 2s. And then 2p, there are 3 of those. So I'm going to draw them over here. So I tend to keep all my p orbitals in one column, all my d orbitals in one column, and all my s orbitals in a column. So after 2p comes 3s. Then we have 3p. And there are 3 of those orbitals, corresponding to m sub l equal -1, 0, and +1. And so there's my 3p orbitals. And then next after 3p comes 4s. And then after 4s comes 3d. So remember, we have this sort of interleaving of these orbitals once they get higher in energy. So 3d is here, and there are 5 of those corresponding to the m sub l values +2, +1, 0, -1, and -2. So each one of these corresponds to a different orbital. And then after 3d, we could keep on following our pattern. So after 3d would come 4p. And it turns out that for vanadium, we won't need any more orbitals than this, but I could continue drawing this picture up. Okay, so now that I have this picture, all my orbitals are empty, and I need to assign 23 electrons into these different orbitals. So first things first, Aufbau Principle. So we're going to start lowest in energy, so I'm here with my 1s. So I'm going to draw one electron that is spin up, so a little up arrow right there. Now my next electron, where's it going to go? Well, it can go in the lowest energy state, spin down, like that, because I have to have those spins opposite. Now I'm done. So that box holds 2 electrons. That little line holds 2 electrons. That's all I can assign to the 1s without violating the Pauli exclusion principle. So Aufbau Principle says, hey, next, move up in energy. So the 2s gets an electron spin up and another electron spin down. Now we're to the 2p's. So next up in energy. So that gets an electron spin up. Now where does my next electron go? Well, Hunn's rule says that the next electron is going to go in the next box, also spin up, and then my third electron can go right there. All right, so now I've added 1, 2, 3, 4, 5, 6, 7 electrons total to my atom, and so I've got this pattern. Now where is my next electron going to go? Well, I still have space in the 2p orbitals, so I'm going to put them there, but now I can start pairing up the spins. So spin down, spin down, spin down. Very good. Next up, 3s. So spin up, spin down. 3p's, spin up, spin up, spin up. Now we do spin down, spin down, spin down, spin down. All right, so those arrows. Now where are we? We're up to the 4s. So spin up, spin down. Good. Let's check on how many electrons we have. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Hey, we're getting close. So 23. So where does our next electron go? So the next electron is going to go up here in the 3d orbital, spin up. So where does our 22nd electron go? Our 22nd electron could go in this box. Oh, by the way, I'm putting it in this next occurring box, but it really doesn't matter which one of these line segments I assign that electron to, because they're all the same energy. So I can mix them up, I just need to make sure that they're all in the same direction. I'm drawing them spin up, but could I draw them spin down? Sure, as long as they are all spin down. So we want to maximize the parallel spins, so they can all be in one direction or the other. So where does my final 23rd electron go? I can put it here. So I could have also put it over here in the -2 box, right here. That would have been fine. Same energy, as long as I do it spin up. So that part doesn't matter. So we just have to make sure we're following those other 3 rules, and then any arrangement that's consistent with that is okay. Alright, so let's do a couple of things now. So I'm going to circle this last electron that I placed on this diagram, and I want to figure out what are the 4 quantum numbers associated with that electron. Alright, so we're going to start with n. So what is the n quantum number? Well, it's in the 3rd shell right here, n equal 3. So the 3 right here means n equals 3. Now L. So remember that these letters tell us what L means. There's a little code, and so that's going to be L equal 2 since we're talking about d-type orbitals. Now M sub L. So I arbitrarily label these boxes +1, +2, +1, 0, -1, and -2. So it really doesn't matter what order I go in. Just know that each box gets its own M sub L value. And since I've labeled this one 0, the M sub L value is going to be 0 for this particular electron that I've circled right here. Now we need the M sub S value. And what is it? Well, I drew the arrow pointing up, so that's spin up, and so that gets a +1/2 for that quantum number. So those are the 4 quantum numbers associated with that electron assigned to this orbital. So let me go back to this last page with Hunn's rule and tell you a couple of things that I didn't tell you before. So anytime we have what are called unpaired spins in an atom, so that would be where we have an electron in a box that doesn't have a partner in the same box that's anti-parallel, so spin up, spin down, right? That we produce something called a paramagnetic atom. So a paramagnetic atom is one that will be deflected in a magnetic field. So it has magnetic properties. So the reason that some materials have magnetic properties are because of these unpaired spins. So if we were to take one of these atoms and pass it through some sort of magnetic field like this, so we've got a north and a south, then as it passes through this field, it's going to be deflected one way or the other. So it's going to be deflected as it passes through this field because it is paramagnetic. Now, if all the spins are paired up in the atom, so there's one up spin for every down spin, then we say that the atom is diamagnetic. So diamagnetic, the dia means not. And so if we take one of those kind of atoms and pass it through a magnetic field, it's going to fly straight through that magnetic field. There's a north pole and south pole without being deflected at all. So this is a kind of atom that will not have particular kinds of magnetic properties. So what is vanadium? Okay, vanadium has unpaired electrons. In particular, it has 3 unpaired electrons. So we would say that vanadium is paramagnetic. And so if we passed a vanadium atom through a magnetic field, we would expect it to be deflected in one direction or the other. So it is paramagnetic. Drawing a picture like this is a good way of assigning electrons to atoms, but it's kind of cumbersome. So we as chemists don't like to draw one of these diagrams for every single atom on the periodic table. So we're going to use a shorthand notation. So this is called an electron configuration. So it just tells us how many electrons we have in each shell and subshell. So an electron configuration. So what I'm going to do is write down the electron configuration for vanadium on this diagram just to show you how it's done. So we start off listing our orbitals in the order that we filled them, following the Aufbau principle. So this 1s orbital right here has 2 electrons in it. So I'm going to write 1s for that electron, then I'm going to put for that orbital, and then I'm going to put a superscript 2 to tell us that there are 2 electrons in the 1s orbital. The 2s orbital, looking over here, also has 2 electrons in it, so I'm going to call that 2s with a little superscript 2. So far, the electron configuration is 1s2, 2s2. Now we've got 2p. So in the 2p orbitals, we're going to count all 3 of these since they're the same energy. We're going to say that there are 1, 2, 3, 4, 5, 6 electrons total in the 2p's. So now we've got 1s, 2s, 2p. Then we look at 3s, 2 electrons there. 3p has 1, 2, 3, 4, 5, 6 again. 4s has 2. And 3d now would have 3 electrons. 1, 2, 3. And so we would say that this is the electron configuration for vanadium. So it's just a shorthand way of representing this picture. So by the way, we've now discovered an important pattern. So s orbitals can hold a maximum of 2 electrons. The p orbitals all together can hold 6 electrons. The d orbitals all together, let's figure out how many electrons they could hold max. So if we look at this d orbital that's up here in my diagram, I could have 1, 2 in this box, 3, 4, 5, 6, 7, 8, 9, 10 all total. So I could have a total of 10 electrons in the d orbitals. Alright, so you might notice that there's kind of a pattern here. So in going from 2 to 6, I added 4. In going from 6 to 10, I added 4. So how many electrons can I fit in all of the f orbitals together? 14. There we go. So there's our little pattern. So this tells us how many electrons total we can have in each one of these configuration things until they're all full. So I could keep going here with the 3d until I get to 3d10, and then I have to move up to the next orbital, the 4p. So now what we're going to do in this section, we're going to write down electron configurations for different atoms. So we're going to start at the very beginning with hydrogen, and right here we're going to have a little table for the number of electrons the hydrogen atom has, and then we're going to write down the configuration. Okay, so hydrogen, we start at the lowest energy level, 1s, and we only have 1 electron for hydrogen. Helium, then, we have 2 electrons, and so we're following the Aufbau principle. So we can stick another electron in that 1s orbital down there, but with the spin going the opposite direction. So that would be 1s2. Next we come in the periodic table to lithium. So lithium has 3 electrons, and so it would be 1s2 still, and then 2s1 would be its electron configuration. Then after lithium we come to beryllium. Beryllium has 4 electrons, and so that would be 1s2, 2s2 for its electron configuration. Then continuing to move across the periodic table, we do boron, which has 5 electrons, and that's going to be 1s2, 2s2. And now we start to fill the 2p orbitals according to our Aufbau Principle and our filling pattern over here. So we're going to start filling up here the 2p orbitals with 1 electron. So that's going to be 2p1. Now we keep moving across the periodic table there. Here's carbon. So carbon has 6 electrons. 1s2, 2s2, 2p2. And then we've got nitrogen. Nitrogen has 7 electrons, so it's going to be 1s2, 2s2, 2p3. Then we have oxygen next. Oxygen has 8 electrons, so 1s2, 2s2, 2p4. And you see the pattern that we're kind of developing. Fluorine has 9 electrons, so 1s2, 2s2, 2p5. And then finally we get to neon, Ne, which has 10 electrons. So 1s2, 2s2, 2p6. So those are the electron configurations then, just following the Aufbau principles for the first atoms in the periodic table. These 2 atoms are in period 1, so that's the first row of the periodic table. This is period 2, the second row of the periodic table. Let's look at period 3. So now we're at the third row of the periodic table. So we're starting with sodium and working our way across to argon. So here are the electron configurations again. So sodium would be 1s2, 2s2, 2p6, 3s1, and so on for the other elements. So the reason I wrote all these out is to show you a pattern. So first off, this electron configuration that's in square brackets right here, you'll notice that that is the same electron configuration that I just wrote down over here for neon, right? Oops, I kind of circled that funny. Alright, so the thing in brackets is the electron configuration for neon. So if we want to save ourselves some work, rather than writing out all of these electron configurations, we can just put neon in brackets here to indicate, hey, we've got the same electron as neon, same electron configuration as neon, plus some other stuff. So this is just like shorthand, so it saves us some writing. So this bracket with neon means same electron configuration as neon, and then 3s1. So magnesium would be neon 3s2, aluminum would be neon 3s2, 3p1, and so on until we fill up all 6 electrons in our p orbitals. Remember, p orbitals can hold a maximum, all total, for all 3 of them, of 6 electrons. Good, so those are the electron configurations. Now, interestingly, if we start looking at these electron configurations and the arrangement of the atoms on the periodic table, we'll notice a pattern. So here I've summarized a partial electron configuration for each of the atoms. So what I'm doing is I'm not showing the last noble gas, I'm just showing the extra stuff, right? So what I'm just going to write is the partial electron configuration. So the stuff past the previous noble gas. Okay, so for hydrogen it's 1s1, helium is 1s2, then lithium starts the same electron configuration as helium plus some extra stuff, 2s1. Then beryllium is 2s2, and so on as we start filling things in. So one thing you notice about looking at the periodic table is it's kind of blocky, right? So we've got this block right here on this side. It's kind of a block structure. And we've got the block in the middle here, the transition elements. We've got another block kind of structure over here in the periodic table. And then there's this block that kind of hangs down here at the bottom of the periodic table, the rare earth elements, also called the inner transition elements. So if you look at the electron configurations, what you notice is that these first 2 columns over here, in all cases what we're doing is we are filling s orbitals. So sometimes this is called the s block. Also notice, interestingly, that in this first column everything has an electron configuration that is s1. And then what we're changing is the n quantum number, and the n quantum number then, the outermost shell, corresponds to the row number on the periodic table, or the period number. So here the number is 1, so we start out filling 1s1. Here the period number is 2, and so we've got 2s1. Everything in this column is s1. Oh, so that's an important pattern. It must be that the periodic table has the shape that it does because of the way that electrons are arranged in orbitals. So now we have a theoretical explanation for the shape of the periodic table. It has to do with the arrangement of electrons in orbitals. Notice then that this second column, these are all ns2. So n is the row number, and this is ns2. Okay, s2, 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 s2. So we're just increasing the row number. Over here, this block, this is called the p block because we're adding electrons to the p-type orbital. And so again, all we're changing, the row number is still the same, the n number. We're just changing the number of electrons in the p orbital. So everything in this column is p1, everything in this column is p2, p3, p4, p5, and then when you get here, it would be p6. Now helium is 1s2, so maybe it sort of goes over here in some ways, but we stick it sort of over here. The first row of the periodic table is a little bit different because that 1s orbital can only hold 2 electrons total until the n equal 1 shell is filled. So that's another interesting thing to notice, that by the time we get over here to column 8a on our periodic table, that we have completely filled a shell. Filled the n equal 1 shell, we filled the n equal 2 shell, and so on. So down here, we've actually not quite filled the 3 shell because they're 3d orbitals, but you get the idea. We've kind of completed a set of orbitals here. So this block here in the middle, you'll notice that what we're doing is we're starting to put electrons in d orbitals. So this is called the d block. Now the pattern here is a little bit different. So you'll notice that we have d1 here for scandium, d2, d3, we've already seen that for vanadium. But chromium, you would expect it to be 4s2, 3d4. Uh-oh, it is not. It is 4s1, 3d5. Why is it that way? Well, because if we put the electrons into the orbitals this direction, this way, we get a lower energy using quantum theory when we calculate it than we would if we do 4s2, 3d4. So it must be then that if you have a 4s orbital and the 1, 2, 3, 4, 5 3d orbitals, that having the electrons arranged like this with all spins parallel, remember Hunn's rule says that's a good thing, that all these parallel spins, that the energy that you get out of that is a little bit better than the Aufbau principle would say by putting that electron at a slightly lower energy, right? So we would think 4s2. But apparently having the parallel spins gives you just enough energy to stabilize this a little bit more than the Aufbau principle says. So this is kind of an exception then to our Aufbau principle. Manganese then would follow our Aufbau principle, 4s2, 3d5. So you notice that there's another exception over here, the 4s1, 3d10. So in that case, copper would have 1 electron in the 4s, and then the 1, 2, 3, 4, 5. Each one of these would have completely filled with electrons. So we'd have 10 electrons. So again, it must be that completely filling that shell gives you some extra stability, because it turns out that quantum mechanics predicts that this is lower in energy than having an electron here. So copper is an exception. You'll also notice that below it silver and gold are also exceptions. Similarly for chromium, molybdenum is an exception, but tungsten is not. Tungsten follows the pattern as we would expect it. So you see that there are a few exceptional electron configurations. For purposes of this class, I want you to memorize the exception for chromium and copper, and those are the only 2 exceptions that I want you to memorize for this course. Okay, those exceptions. So this is the D block, and then down here you'll notice that we start having electron configurations where we're putting things in f orbitals. So this is sometimes called the F block. Notice that the D block, how far across the D block do you go? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, aha, we know that we can fit a total of 10 electrons in d orbitals. What about these f orbitals? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Hey, we know that we can fit a total of 14 electrons in the f orbitals. So the arrangement of the periodic table then helps us figure out the electron configuration of the atoms. Or the other way around, it is the electron configuration of electrons and atoms that determines the shape of the periodic table. And we know that the periodic table is found to have this shape from experimental data based on their properties. So it must be that electron configuration has an awful lot to do with the behavior and the properties of these atoms.